Hey guys, welcome back. We're going to talk about solubility and solubility product. All right, so just so we know, that's going to be KSP and QSP. If you remember K and Q for equilibrium constants and reaction quotients, same thing. So heterogeneous equilibria, different phases, right? So some salts, which are, of course, ionic compounds, right, are almost insoluble. What do we mean by that? So if you took potassium hydroxide, and we're going to put this per 1,000 grams of water. So if I have 1,000 grams of H2O, how many grams of potassium hydroxide can dissolve? Well, at 25 degrees Celsius, it's 1,430 grams, which is a lot. Sodium chloride. Again, sodium chloride, for our 1,000 grams of water, we can get 357 grams of sodium chloride, which is a lot. Not as much as potassium hydroxide, but a lot. Then we have calcium carbonate, which some of you might know is the main component, like chalk. You would write on the sidewalk or the chalkboards, if you ever see those. So for every 1,000 grams of water, we actually only get 0.008 grams or 8 milligrams of calcium carbonate. All right, that's not a lot. So what do we mean by this? So if we look at calcium carbonate here, CaCO3, well, that's a horrible 3, solid. Right, we got the double arrow, calcium 2 plus CO3 2 minus. All right. So what happens here? We have very low concentrations of ions in solution. Very low, right? However, what does dissolve, all right, and dissociates is a strong electrolyte. What does that mean? I thought strong meant that it completely ionizes. Well, what strong means is, in this case, it's a good conductor, right? It conducts well. So those ions will contribute to good conductivity, right? And what we say, this is a sparingly soluble salt. Right? So now, just to recap, before we continue, let's look at our general solubility rules. All right, and this little table. This is not everything. But these are just some good general ones to know. And if you look, group 1 and ammonium are soluble. Okay, so these are water-soluble compounds. So lithium, sodium, potassium, rubidium, cesium, and ammonium, they're soluble. So if you see those, they're almost always soluble. I'm sure you can find some exceptions. That's not what we're talking about. We're talking about that in general, you see a sodium salt, it's going to dissolve in water, right? Nitrate is a big one. We use a lot of nitrates. Acetate and chlorate, they're soluble. All right, they're just soluble. Now, the halogens, all right, are generally soluble. However, silver, mercury 1, this is mercury 1, right? It's 2 mercuries at 1 plus. Lead 2, they're not soluble. And sulfates are generally soluble. However, silver, mercury 1, lead 2, calcium, strontium, and barium, they're not. So those are just some general things that are soluble with a couple exceptions. And then general insoluble salts. You have carbonate, phosphate, chromate, sulfide, hydroxide. These are generally insoluble. But the exceptions, if you notice, these are the exceptions. Right? There's a couple more, like barium's in there for hydroxide. All right? But these guys are the soluble ones. All right? So those are just the general solubility rules. I don't expect you to know and memorize all those things, but for you, especially if you're going to continue on in chemistry, to know that most of group 1 is soluble. Ammonium soluble. It's good to know, right? That's actually a good thing. Okay, so let's do an example here. I'll come back up here. Example. Silver chloride. And I'm going to be honest with you guys. The hardest part of this for many of my students, not all of them, but many of the students, is writing down this chemical formula. What is silver? What is chloride? It's a Chem 1 topic. All right, hopefully you learned how to write the formulas from the names. If you haven't, you're going to need to review that. All right, so we got silver chloride, AgCl, solid, all right? And if you need to, there is no shame. Silver is Ag plus, chloride, Cl minus. There's no shame in doing that, all right? So silver chloride, and we got our arrows, breaks up to a silver ion and chloride. All right. And so what's important, this is solid and this is solution, which means we have different phases here. All right, that's why it's heterogeneous. All right. And so what we do is we write the equilibrium constant expression for those components in solution. All right. With respect to the system in solution, all right, the amount of solid in this case solid silver chloride present is irrelevant. As long as at least some is present, some solid is present when equilibrium is reached. So that means for KSP here, all right, will be the concentration of silver and chloride. Now, we call this solubility product. And most of these KSPs, like in this case, KSP is 1.77 times 10 to the negative 10th, all right? And most of the time when we talk about solubility, we're talking molarity. Now, technically speaking, if I scroll back up on you guys, These are also solubilities. Those are solubilities as well. Mass per mass. That's a way to express solubility. But when we talk about KSP, almost always we're going to be talking about molarity. All right? Okay? So that is what's kind of important. Now, I believe if I scroll down here, I have the example written. Yes. What is the solubility? All right, so there's the question. What is the solubility of silver chloride? And so we're looking for the molarity. If KSP gives you KSP is 1.77 times 10 to the negative 10th. All right. Well, here's how I would do this. Write down your silver's Ag plus, Cl minus, like we just did. So you have AgCl solid. Then you have your arrows, Ag plus Cl minus. And KSP then is equal to, as we just did, Ag plus Cl minus. All right, so silver and chloride. Now, ice table. Silver, as long as we have some, nice little box there, as long as we have some, we don't care. How much do we have? You start with 0 and 0, plus x, so you get x and x. Plug in. 1.77 times 10 to the minus 10th equals x times x. So 1.77 times 10 to the negative 10th equals x squared. So it means x equals the concentration of silver chloride, which is the concentration of silver ion in this case, and the concentration of chloride. And our x, if we get out the calculator, square root of 1.77 times 10 to the negative 10th. I'm getting 1.33 times 10 to the negative 5th. So that's what I get for how much silver chloride will dissolve at, of course, this is at 25 degrees Celsius in chemistry land. There we go. All right. The next one, if the solubility of silver iodide is 1.22 times 10 to the 8 molar, what is the value of KSP? So now we got the solubility of silver iodide is that, right? What is KSP? Well, silver iodide, silver, Ag plus, iodide, I minus. So we have AgI solid, Ag plus, and I minus. Our expression, KSP, is equal to silver and I. All right. Well, we don't know what KSP is, but we know the concentration of silver iodide is 1.22 times 10 to the negative 8 molar, because it's 1 to 1 to 1. If I were to, my ice table here, those lines don't look parallel to me and it bothers me, I'm sorry. There we go. We know that this is 1.22 times 10 to the negative 8 molar and 1.22 times 10 to the negative 8 molar, right? That's what we that's what we got. All right, so what do we do with that is the question. Well, we know that we had some silver iodide, right? We know it was 0 and 0, And then we knew we have these concentrations. So all I need to do is take these two concentrations and plug them in. All right. So KSP is going to be 1.22 times 10 to the minus 8 times 1.22 times 10 to the minus 8. Means KSP is what? Let's see, 1.22 times 10 to the minus 8 squared. I get 1.49 times 10 to the negative 16th. All right. All right. So now, another example. And we're going to let you know the stoichiometry, or the solution, or the situation, the situation is a little more complicated. All right, the stoichiometry of the salt is not 1-to-1. What does that mean? Well, let's look at this example of silver chromate. All right. So what is the solubility of silver chromate? And it gives you KSP. Well, first thing we got to do, silver, Ag plus, chromate, CrO4 2 minus. All right. Well, what's the formula? So we have Ag2CrO4 solid. And we get 2 silvers plus Cl minus. Not Cl minus, holy cow. Let's go with chromate. Sorry about that. All right, so ice table. All right, again, as long as we have some, we're good. 0, 0. It's been plus x and plus x, but it's actually 2x here, right? So at equilibrium, we got 2x and x. The KSP expression is silver ion squared times chromate. All right. And so if we plug these numbers in, we have 1.12 times 10 to minus 12 equals 2x squared times x. And I'm going to zoom in on this right here. And this is where, at least me, I would rush this step and not take a time to breathe and do silly things here, all right? So this math is not hard. 1.12 times 10 to the negative 12th. But we're going to fall into the trap. I would fall into the trap of like 3 times 2 and put 5 down, right? This is the same thing, except we're doing with, x and powers. What does this come out to be? You got to take your time. 2 squared is 4. Then I have x squared times x, 4x cubed. I've seen 2x cubed, I've seen 4x squared, I've seen it all right? And it's a small detail, but it's kind of important, right? Obviously. All right, now we have to do this, we take our 1.12 times 10 to the negative 12 and divide that by 4. And we get 2.8 times 10 to the negative 13 equals x cubed. And so now we got to take the cube root. All right, or to the 1/3 power. However you want to do it. I get 6.54 times 10 to the negative 5th for x. No, let's use the purple. Come on. Now, molar, right? Now, x equals what? The concentration of chromate and silver chromate. What does the concentration of silver equal? 2x. All right? And so concentration of silver ion would be 1.3, what would it be? Yeah, 1.31 times 10 to the negative 4 molar. Zooming back out. All right. And so that would be the concentrations of these ions. So it would be 1.31 times 10 to the negative 4 molar and 6.54 times 10 to the negative 5 molar. All right, so those are your concentrations at equilibrium for this because it's not 1-to-1. So it almost looks like you're doing it twice with 2x and it's squaring it, but you're not doing it twice. That's just how it works. All right. So now let's do a couple examples. All right. Write the expression of KSP of these compounds. So silver chloride, again, Ag plus, Cl minus, right? And so I would say this is AgCl. And so you have, if you need to, you don't have to do this because this is the reaction. So, but the KSP is equal to silver ion and chloride. So that's what we're looking for here. All right, but you might have to write it out. Lead 2 iodide, Pb2 plus, I minus. So we have PbI2. All right. Now, if you can just write out what KSP is, feel free. But my recommendation, especially as we're learning, is to do this. So our KSP expression would be lead 2 and I minus squared. Calcium phosphate. Well, calcium is Ca2 plus, phosphate PO4 3 minus. So Ca3 PO4 2. All right, and I would definitely, the more complicated they are, write them out. Okay, there is no shame in writing these out. 3 calciums, 2 phosphates. So KSP would be concentration of calcium ion cubed and phosphate squared. All right, it's very easy to mess this up if you don't take your time. All right. Finally, chromium 3 hydroxide, Cr3 plus, OH minus. So we have CrOH3. So CrOH3 solid, chromium 3 hydroxide. We're going to get chromium 3 plus and 3 hydroxides. That means KSP, chromium 3 concentration, and hydroxide concentration cubed. Oh, there we go. All right. A saturated solution of calcium phosphate. Ooh. Has a calcium ion concentration of 2.01 times 10 to the 8. And so we got calcium. All right. So we're going to have calcium. And phosphate. And we're going to calculate KSP for calcium phosphate. Well, luckily we just did this one. So we have Ca3PO42 solid, Ca2 plus, and there's 3 of them, plus 2PO43 minus. And your KSP expression is your calcium ion cubed and our phosphate ion squared. All right, so now we know at equilibrium, at E, calcium was, or is, 2.01 times 10 to the minus 8 molar. Ooh, that's ugly. Let's try that again. And phosphate is 1.6 times 10 to the negative 5 molar. All right, let's plug it in. And so we have 2.01 times 10 to the minus 8 and 1.6 times 10 to the minus 5. All right, so calculator time. 2.01 times 10 to the minus 8, and that is cubed, times 1.6 times 10 to the negative 5, and that's squared. I get well, I only have 2 sig figs, 2.1 times 10 to the negative 33. Hopefully that's what you get as well. All right, number 3. All right, we have not done this one yet, so we're not going to do that. We're going to end